Good afternoon again, everyone. My name is Linghui from the Hong Kong University of Science and Technology. Today I will present our work on an ontology-driven framework for intelligent embodied carbon design support in metro station design. The key idea is simple. We want to move from automated carbon assessment to interactive carbon design support. So the framework is not only a carbon calculator, it also helps engineers and designers ask questions, check evidence, and test design alternatives in a more reliable way. So let me start with the background. Metro systems are important for sustainable urban mobility. But building metro stations, especially underground stations, can create very large embodied carbon emissions. This is because underground construction involves many carbon-intensive works, such as excavation, temporal support, concrete structures, waterproofing, transportation, and construction equipment. Another important point is timing. Many carbon-related design decisions are made in the early design stage, but at that stage, detailed construction data is often not complete. Current BIM-LCA methods have two main problems. First, they are usually element-centric. They work well for visible and permanent BIM elements, such as walls, structural walls, slabs, and columns. But they often miss implicit processes such as earthwork, formwork, temporary structures, and logistics. Second, many tools only provide static results. They can calculate carbon, but they do not really support interactive decision making. So our research question is, how can we infer missing construction logic from sparse BIM data and then support safe and auditable carbon interaction? The literature review can be summarized into three streams. The first stream is BIM-LCA integration. Existing methods improve quantity takeoff and carbon calculation, but most of them still depend on explicit BIM objects. IFC-based workflows are more open and interoperable, but they are still difficult to apply to complex underground infrastructures. The second stream is ontology in AEC domain. Ontologies are useful because BIM and LCA describe the world differently. BIM is object-based and geometry-based, while LCA is process-based and resource-based. Ontology can connect these two logics through shared concepts, rules, and relationships. The third stream is large language models in AEC. Large language models are becoming useful for information extraction, workflow planning, and design support. But in engineering calculation, unconstrained large language models are risky. They may hallucinate, make invalid assumptions, or produce wrong calculations. So these three streams lead to our methodology, an ontology-constrained carbon intelligence framework. This slide shows the overall architecture. Our framework has three layers. Layer 1 is a semantic foundation. We build a domain ontology called MSCA on top. It defines how metro station systems, elements, construction processes, resources, and carbon emissions are connected. Layer 2 is automated quantification. Here we use topological reasoning and geometric reconstruction to infer hidden or implicit construction quantities. Then we generate a carbon knowledge graph. Layer 3 is the interactive interface. We use a large language model-based multi-agent system, namely MAS, to allow users to query data, correct knowledge graph, and conduct scenario analysis. The assessment boundary includes cradle to construction carbon, so we cover production, transportation, and construction stages. Physically, we include the main structure, implicit earthwork, and temporal enclosure, or retaining systems of underground metro station. The main shift is from static geometrical extraction to knowledge-enabled inference and interactive design support. Now we will explain the ontology. The ontology we proposed is built around the SEPRC structure, namely system, element, process, resource, and the carbon. The system module describes the metro station and its engineering system, such as the foundation pit, enclosure system, and mass structure. The element module describes the physical components, such as structural slabs, walls, columns, tiles, and the bracing elements. The process module is very important. It connects elements with the construction work packages, such as concrete work, formwork, earthwork, transport, and demolition. The resource module describes the materials, equipment, energy, and logistics parameters consumed by those processes. Finally, the carbon module calculates and aggregates emissions at different levels. The key point is that we do not directly map a BIM element to a material only. Instead, the element triggers a construction process, and the process consumes resources. This better matches how construction carbon is actually generated. This slide shows an implementation view of the ontology. After the ontology is applied to project data, we generate a carbon knowledge graph. This graph links system, element, process, resource, and carbon information together. The benefit is that traceability. If we see a carbon result, we can trace it back to the resource, the construction process, the element, and the engineering system. This is important from design support because engineers do not only need a total carbon number, they also need to know where the carbon comes from and where it can be changed. Next, I will introduce the automated OpenBIM pipeline. The pipeline takes raw IFC models and geological data as input and transforms them into a carbon knowledge graph, as we mentioned before. There are three major steps. First, we build a reference knowledge basis. The construction process databases, or CPD, stores unit resource consumption for construction methods. The emission factor database, namely EFD, stores carbon factors from project-specific, regional, and generic sources. Second, we perform hybrid topological reasoning. We first classify BIM elements using attributes and text similarity. Then we calculate spatial relationships such as containment, adjacent, and vertical positioning. These relationships help us understand the real engineering role of each element. Third, we reconstruct the foundation pit geometry. This is important because excavation work is often not explicitly modeled in BIM. We extract the enclosure envelope, build vertical surfaces, and generate excavation and backfill volumes. Then we intersect these volumes with geological layers to calculate earthwork quantities. So after the carbon knowledge graph is built, we use a MAS, namely multi-agent system, to make it interactive. The main principle is large language model can understand the user intent and plan the task, but deterministic tools and ontology rules must execute the calculation. The task, this is some agent collaborating with each other to finish their task. We also developed a web prototype. The system has a pattern backend IFC passing with IFC OpenShell and IFD triple store for the carbon knowledge graph. So the result is, okay. So for validation, we used 8 metro station projects in Guangdong province, China. The dataset includes more than 23,000 BIM components. We also evaluated the MAS using 150 practical queries across retrieval, correction, and strategic analysis tasks. The result showed that the proposed pipeline is close to expert calculation and reduce some time. like this. So now let us look at the MSE benchmark. The best performing backbone achieved about 80% average correct rate across the 3 task types. So this is some failures in different steps. So in discussion, I want to highlight 3 implications. Theoretically, this work reframes metro carbon assessment as a SEPRC reasoning problem. It moves beyond the simple element to material mapping. Technically, it combines topological reasoning, geometric reconstruction, carbon knowledge graph generation, and sandbox to execution. Practically, it reduces manual work, exposes hidden hotspots, and allows engineers and designers to ask natural language questions while keeping the process auditable. So this is the conclusion. That's all for my presentation.
Thank you very much.